Okay, so I cannot show the first slide, but it's okay. It's a pleasure for me to be here once more. I came in this place very often and I always like it. I am thankful for the chairperson for the kind words he said, for the three main organizers who did a great job, for the two recipients of this session, the two heroes of the day, Srini and Kalyan. And also I am impressed to see so many volunteers who are here to help us, a dozen of them. That is very, very well done. And so thanks to all of you. And since we are a bit late, I will start immediately. And so the title of my talk, the title of my talk is Variation on Schanuel's Conjecture for Elliptic and Quasi-Elliptic Functions. It's a joint work with Christiana Bertolin. It's not final, but first of all, if you want to see the slides, they are on my website. And also, if you want to see the final version, I plan with Christiana Bertolin to submit it to the proceedings of this conference, which are supposed to be published by the Hardy Ramanujan Journal. Okay, so Schanuel's conjecture is a well-known and far-reaching statement involving the exponential function, and our goal is to study what would be the suitable conjectures involving elliptic and quasi-elliptic functions. So the Weierstrass function sigma, zeta, and p, and also some functions which were introduced by Serre in connection with elliptic integrals of the third type. So the conjecture of Schanuel is that if you have linearly independent complex numbers x1, xn, linearly independent of a q, then when you look at the 2n numbers x1, xn, exponential x1, exponential xn, these two n numbers, among them, at least n are algebraically independent, which we can phrase by stating that the transformant degree of the field generated by the two n numbers is at least n. So this conjecture started with a course given by Serge Lank in Columbia in the 60s. This course was attended by several mathematicians, including Nagata and Schanuel. So Schanuel suggested this and did not publish the conjecture himself, but this was published in the book of Lang on transcendental numbers. And there was another problem which is well known, which was suggested by Nagata, who attended the course by Lang. And this conjecture of Nagata was solved by Enrico Bombieri a bit later. The conjecture of Schanuel is famous for including most of the statements that we expect to be true for the transcendence values of the exponential function and for the logarithm. And just to give one example of a consequence of Schanuel's conjecture, I would like to explain how it would solve a problem which was asked to me by Federico Pellarin. He asked the following: we take fixed points of the exponential function, which means that there are complex numbers zi, which satisfy the equation exponential of zi equals zi. We assume that they are distinct, and the question is it true that they are linearly independent of a q? So some remarks on this problem. The first thing is that the entire function exponential z minus z has infinitely many zeros. You can see it by saying that if it had only finitely many zeros, it would be a polynomial times an exponential, and you can deduce the result that this is not possible. Another way is to look at the so-called Lambert function, which is the function w of z, which is defined implicitly by exponential w times w equal z. And this function is well known, and there are several branches because it's not univalued. And there are some values which give the values -1 for Lambert function, which gives a fixed point for the exponential function. The next thing is that if you have a fixed point, z equal exponential of z, because z is an exponential, it is not zero, and z cannot be algebraic because of the Hermite-Lindemann theorem, which states that if alpha is algebraic non-zero, exponential of alpha is transcendental. So for 1 point, we have the result. For 2 points, it works also. if Z1 and Z2 are fixed points of the exponential function, if the quotient was a rational number, then we write the equation A1Z1 equal A2Z2, and we deduce that Z1 power A1 is exponential A1Z1 because Z1 is exponential Z1, and then A1Z1 is A2Z2, and exponential A2Z2 is Z2 power A2, and finally Z2 is Z1 over Z2 A1 because of this equation. And so we find that Z1 satisfies polynomial equation, which is not trivial because the constant term is A2 power minus A2. So for two numbers, it's okay, but I am not able to go further than this unless I use Schanuel's conjecture. And we want to prove that, so the result of Schanuel conjecture is that if Z1, Zn are distinct fixed points of the exponential function, then they are algebraically independent. It's more than linearly independent, but in fact it is equivalent because they are fixed points of the exponential function. And so it's sufficient to prove that Z1, Zn are linearly independent. So we assume that we have a linear relation between the fixed points, which are distinct. And by induction, we can assume that all the AI are different from 0. Now we use the fact that Zi is exponential of Zi, so we have a relation, a monomial relation between the Zi. And so using exponential Z1 equals Z1, and the same for the other, we have two algebraic relations between the Z, a linear one and a monomial one. And it's easy to see that this is not possible by the induction hypothesis, using the fact that N1, Zn minus 1 are algebraically independent by induction. And so we eliminate Zn, and we have a polynomial relation involving Z1, Zn minus 1, and the top constant term is non-zero, so we get a contradiction. So this is just an example to show the power of Schanuel's conjecture. Very few results are known. The most important result which is known is if you take Z1, Zn, or X1, Xn, which are algebraic and Q-linearly independent, then the fact that the exponential are algebraically independent is a result of Lindemann and Weierstrass. And this is almost the only important result in this direction. There are two other results of algebraic independence that we can quote. One is by Gelfond that, for example, 2 power cube root of 2 and 2 to the power cube root of 4 are algebraically independent. So it's a restrictive result, but it's a result of algebraic independence. And Nesterienko that the two numbers pi and exponential of pi are algebraically independent. So these are consequences of Schanuel's conjecture, and there are not so many other results of algebraic independence that are known. So I would like to add one item to the list of results which are known, and it is by looking at what happens for almost all numbers. And so I introduce the definition. A tuple of complex numbers satisfies the strong Schanuel property if the two n numbers are algebraically independent. So, of course, not all tuples of complex numbers satisfy this property, but the first result of this talk is that almost all tuples of complex numbers for Lebesgue's measure satisfy the strong Schanuel property. And the proof is not deep, and I will come back a little bit to the proof. It is just the fact that the exponential function is a transcendental function. And the transcendental function means a transcendental over the field C of Z. And the result is true if you replace the exponential function, which occurs here, by any transcendental function. And so what we could do is, with in the paper with Christiana Bertolin, we will give explicit examples of n tuples which satisfy this property. These explicit examples are obtained by using Liouville numbers, so numbers which are very well approximated by rational numbers. So far, we have a very strong condition on Diophantine approximation, but nevertheless, it gives uncountably many explicit examples. There are many situations in number theory where we know something is true for almost all numbers, but we are not able to give an explicit example. So here we can give an explicit example. So I told you that we can replace the exponential function by any transcendental function. And more generally, if we take functions which are meromorphic in C, which are algebraically independent of a field K, and K is any field, subfield of C, which is finitely generated over Q, for almost all tuples of complex numbers, the empty numbers Fj of Zi are algebraically independent of a K. So this is a general result, which is not too difficult to prove. The proof uses three facts. The first one is that if we have a non-zero meromorphic function of n variables, when we look at the set of zeros of f in Cn, it's an analytic variety of dimension n-1, and so the Lebesgue measure is 0. So this is the first fact. The second one is that a countable union of sets of Lebesgue measure 0 has Lebesgue measure 0, and the third is the set of zeros of f. The first fact is that f is not the zero function, because the fj are algebraically independent. And so the set of tuples so that the empty numbers are algebraically independent of a k is a union of all the set of zeros of these functions, where p runs over the countable set of polynomials in empty variables. And so we get the result. Now, the result which I mentioned is true for any set of functions. We cannot get something very strong if we do not specify the functions. For example, it is possible to construct algebraically independent functions, f1, ft, like in the statement before, such that for all algebraic z, all the fj of z are algebraic. So the transcendent degree may be 0 if we take suitable functions. So we have to restrict to interesting functions. And what we do is to consider elliptic and quasi-elliptic functions. So the function that we consider, first we take the sigma function attached to a lattice in C and to an elliptic curve C over omega. This is the canonical product of Weierstrass, the function, the simplest function to a certain extent, which vanishes at all the points of omega. Next, we take the logarithmic derivative, which is Weierstrass zeta function. And after that, we take the derivative of zeta and with the sign minus, and we get the p function, which is an elliptic function. We will add a further function, and I will explain why, which was introduced by Serre in around 78. And for each q which is not a period, we consider fq of z, which is sigma of z plus q over sigma of z, sigma of q, exponential minus zeta of qz. So these functions will play a role which I will explain. So the periods of the Weierstrass elliptic function, which are omega 1, omega 2, are elliptic integrals of the first kind. The quasi-period of the zeta function, zeta of z plus omega minus zeta of z, are given by elliptic integrals of the second kind, and the functions fq were introduced by Serre to study the properties of elliptic integrals of the third kind. This function satisfies periodicity and quasi-periodicity relation. When we prove it, we first prove that p is a periodic function, it's an elliptic function for the lattice omega. From that, it follows that zeta is quasi-periodic with eta of omega. And from this relation, we deduce the quasi-periodicity relation for the sigma function with epsilon, which is plus or minus 1, and we have an exponential. And finally, the function of Serre. So the zeta function, it's an additive period, and here it's a multiplicative period. We have the exponential of this number, omega zeta of q minus q eta of omega. So these are the periodicity which will be used in the result which I am going to prove, just, well, to explain, not to prove right now. So the theorem that we can prove is that if we take complex numbers which are linearly independent of a Q, we take a Q1, Qs which are complex numbers such that omega 1, omega 2, Q1, Qs are linearly independent of a Q, and we consider all these functions, then all these functions, the number of them is S plus R plus 4. We have 4 here, we have R here and S there. All these functions are algebraically independent. It is necessary to assume that omega 1, omega 2, and Q1, Qs are linearly independent. Otherwise, the result will not be true. So we have a lot of functions which are algebraically independent. And for the proof of this, we just use the periodicity which I mentioned before. For the periodicity, you see in this function, there is one which is a sigma function, which is a function of order 2. And the other functions are all functions of order 1. So we first eliminate the sigma function by looking at what happens when for sufficiently large z. And then we use the periods of p. So p will just stay constant. And we have to look at what happens with the periods which are here. And so for the proof, we need a lemma, which I give here and which may be of independent interest. We ask when there is a polynomial in z1, z2, x1, xs, so which satisfies this relation. In the simplest case, this amounts to a van der Monde determinant, but we have a generalization of the van der Monde determinant. And the result is that such a polynomial exists if and only if the points q1, v1, qs, vs, which are in C square, the non-zero element of C square, if and only if they are multiplicatively independent. Just a word to say that multiplicative independence is just the notion of linear independence in linear algebra for an abelian group, which is a Z module, but which is written multiplicatively. So the condition which is here means that there is K1, Ks, the multiplicatively dependent means that there is a non-zero K1, Ks, so that we have the relation here. So I do not say more about the proof of the result, but from this proof we deduce something which we can phrase as the strong elliptic Schanuel property. We take the same function as before, and we take variable zi, and the result is that if we take t1, tr, which are fixed for the exponential here, which are complex numbers linearly independent of a q, q1, qs, which occur here, are complex numbers so that omega 1, omega 2, q1, qs are linearly independent of a q. This was exactly the condition for the algebraic independence of the functions. So if we have algebraically independent functions, then for almost all tuples, z1, zn, all these numbers are algebraically independent. So we have a statement which is not a conjecture, but now we would like to have a conjecture which is valid for all tuples, not almost all, but all tuples, like in Schanuel's conjecture. We have n free parameters, z1, zn, and in the case of Lindemann-Weierstrass, we take the zi, which are algebraic, and so the transcendence degree is only n. Here it's the same. The conclusion of the conjecture, we had n s plus r plus 4, but we cannot expect that transcendence degree for all the z1, zn, so we will have n less, so n times s plus r plus 3. So this should be the conclusion. We cannot expect better than that. Now, the result was with a field which is finitely generated of a Q. We cannot take any field, we have to take a number field, and we can take Q of G2, G3, which is what we will do. Then we need some assumption on the Zi. The previous result was for almost all Zi. In this case, they are linearly independent. But here we need at least that they are linearly independent over the field of endomorphism of P. Otherwise, we have trivial relation. And also, it is natural to assume something on P of Qi. And so if we put all that together, we can get some statement. But if we want to have a good ground to state a conjecture, the best solution is to take a geometric point of view. So I give a statement which we consider as a semi-elliptic conjecture of Schanuel. And to make things easier, I assume that there is no complex multiplication. In the case of complex multiplication, it will be slightly different, but not much. So we take the Pi, which are complex numbers linearly independent of a Q, the Qi with the same assumption as before, omega 1, omega 2, Q1, Qr are linearly independent of a Q, and we have Ts, which are linearly independent of a Q. And then the conjecture is that if we take all the numbers which are here, 3n plus r plus nr plus 2s, this is the number of elements which I write here, at least 2n plus nr plus s should be algebraically independent of a Q of G2, G3. So this is a conjecture that we suggest, and we have some reason to suggest such a conjecture, which comes from geometry. So we consider the algebraic group G, which is an extension of the elliptic curve by the multiplicative group, which is parameterized by a point which is the exponential of Q on the dual elliptic curves. So the Q occurs like this to parameterize the extension of the elliptic curve. The fact that Q is not of torsion means that the elliptic curve, the extension is not trivial. And then there is an exponential, there is an algebraic group, which is a G, which is a Lie group. So it has a Lie algebra, and there is an exponential. And the exponential is parameterized by the sigma function, the P function, and the exponential, and the FQ function, which occurs here. So this parametrization is explained in the book by David Masser. He has a chapter on the elliptic functions, which is which contains a lot of things. And now, using this geometric point of view, there are some conjectures. The first one was Schanuel, then there was Grothendieck, and then, maybe Grothendieck was before, but and then Yves André generalized the conjecture of Grothendieck and Schanuel, and he phrased a general conjecture on periods and generalization to motifs. And the case of one motif was developed by Christiana Bertholin, and she called this ellipticotoric conjecture. So it's based on this conjecture that we propose this elliptic, semi-elliptic conjecture. To conclude, I would like to quote something which is related with a kind of joke of David Masser. There is a recent paper by Senthil Kumar, which was published in Acta Arithmetica, and David Masser wrote an appendix to the paper of Senthil Kumar, and the appendix has the title Rational Values of the Weierstrass zeta function. And David Masser points out that the result in the paper by Senthil Kumar has a consequence, which is that if the two invariants G2 and G3 of the elliptic functions are algebraic, then for the Weierstrass zeta function, one at least of zeta of 3 and zeta of 5 is a transcendental number. And we conjecture, in fact, it's a consequence of our conjecture that both of them, zeta of 3 and zeta of 5, should be transcendental. But David Masser writes, this may be found amusing by those who study another zeta function, and he adds a theorem which is that there exists invariant G2 and G3 such that both zeta of 3 and zeta of 5 are rational numbers. And from the result of Senthil Kumar, it follows that G2 and G3 cannot both be algebraic. So, based on this joke of David Masser, we propose the following result, which includes the Weierstrass and the Riemann zeta function. So we denote by zeta A the Riemann zeta function, and the first proposition is that if you consider the four functions z, p of z, zeta of z, and zeta A of z, we have four functions, and these functions are algebraically independent. The proof is not too difficult. We use the fact that for the Riemann zeta function, if you take z with real part which tends to infinity, then zeta of z is very close to 1. So essentially, we eliminate z by taking z sufficiently large, and then we are back to the algebraic independence of z, p of z, and zeta of z, which I mentioned before. And so, as a corollary, for almost all tuples of complex numbers, the 4n numbers which are here are algebraically independent of a Q of G2, G3. I started by giving a result that we are able to give an explicit example for the strong Schanuel's conjecture for the exponential alone. I must say that here I know that this is true for almost all n tuples, but we are not able to give a single example of such a tuple. And it's probably rather difficult to give it, even to give an example where we take only one of them, that the transcendence of zeta of z and zeta r of z is something which is essentially hopeless. So thank you. We have time for questions.
Thank you, Professor Waldschmidt, on a beautiful lecture on a really fascinating topic. Thank you. Any questions for our speaker?
So in which context does SAR define this function, this particular function you were looking at? SAR's function.
FQ of z?
Why SAR looked at this function?
Yeah, the function, you mean the function
FQ.
FQ of z?
FQ, yeah, f of q.
Well, in fact, I gave a course in the Collège de France in 1978. I was invited by Serre, and during my course, I explained that we have the function z, p of z, and zeta of z, which are used to parameterize the elliptic integral, the first and second kind. And I said we do not know a function which would play the same role for the elliptic integral of the third kind. And Serre immediately told me, oh, this was known in the 19th century. And the next week he came back and said, I did not find a reference, so I wrote the result, and it is published in the appendix of my book in Asterisk.
I think the very last slide, in a way you eliminated the Riemann zeta function from the picture. Can you please explain how it reduces to the first three functions, that the last one does not matter so much, something like that?
You mean this one?
The algebraic independence of 4 functions.
Yes.
You said the Riemann zeta function in a way is dropped or eliminated and
Yes.
reduced. Can you please explain how that...
Yes. We assume that we have a polynomial in 4 variables, such that the function p of z, zeta of z, and zeta r of z is a 0 function. So this is the assumption that we start with. And so what we do is that we take z, which is sufficiently large, and we replace zeta r of z by 1 plus something which is very small. And so we divide the polynomial by, say, the last variable is x4. We divide the polynomial by x4 minus 1. And so we have zeta r minus 1 times something plus a remainder. And then zeta r minus 1 is something which is very small. So using some elementary analysis, complex analysis, we deduce the result.